Hello, everyone, and welcome to our meetup about the visitor design pattern and the new modern way of implementing it in Java. So, during the last years, new features were added to the Java programming language. Record classes, pattern matching, sealed classes, and many others. Well, these three allow us to implement the visitor design pattern in a simpler way compared with what we are familiar with. So this is the plan for today. First, I want to introduce the programming problem for which the visitor classic design pattern was developed. After understanding the intent of this design pattern, we will go over the traditional implementation, the one you are probably familiar with if you are familiar with the Gang of Four book. After that, we will go over another version of this design pattern. I call it the modern implementation, the one that use records, sealed classes, and pattern matching. What we are going to see today isn't relevant only for not it's not is relevant not only for Java, but also for other modern programming languages, including C Sharp, Kotlin, and others. After all, pattern matching is well supported in many programming languages, and the same with record classes. In some cases, in some programming languages, they call it data classes. Then we will summarize our meeting by going over the benefits of using records, seal classes, and pattern matching. Okay, so let's start with understanding the the programming problem for which the visitor design pattern was developed. Well, in many software development, in many systems, in many applications, we might find a collection of objects. Usually it will be a collection, or the object will be organized in some sort of binary tree or a graph of objects. And in those cases, it is common that we would like to traverse those objects and perform an operation on each and every one of them. It can be rendering those objects to the screen or evaluating those objects one by one, and so on. Now, one option is to add that operation, that rendering operation, or evaluation, or something else to the classes from which the objects were created. And usually those classes will be part of a hierarchy, class hierarchy. And this is an option. We can do so. However, taking this approach, we might clutter the new code with unrelated logic, and the code might become a bit complex, not to mention that it might become a violation of one of the well-known principles in object-oriented programming, one of the first of the solid principles, single responsibility principle, SRP. That principle says that we don't introduce changes in our code, in the code of a class, for instance, unless it is for accomplishing the target for which the class was defined. So code that render the object to the screen, we should consider it as a code that should be in another class, not the classes from which the objects were created. In addition, if we choose that approach, adding simple methods to classes we defined, it means that whenever we want a new operation, to have a new operation that we can invoke on each and every object, that will require adding the code of that operation to each and every one of these classes. And when dealing with a big number of classes, it might become too much. So we are looking for a solution. We are looking for having a way to add new operations that we can perform on each one of these objects we have in a binary tree or a collection without changing the code of those classes from which those objects were created. So for solving this problem, the visitor design pattern was developed. So we can put it in simple words. The programming problem for which visitor was developed is how to define new operations on a set of related objects, such as objects that are created from various classes that belong to the same hierarchy, without modifying their source code and without duplicating logic across types. So in bottom line, without changing the code of those classes from which the objects were created. Well, if you check the Django 4 book, this is the text you can find. This is the intent for which the visitor classic design pattern was developed. Represent an operation to be performed on the elements of an object structure. Think about binary tree or collection. Visitor lets you define a new operation without changing the classes of the elements on which it operates. So let's look how the visitor design pattern actually decouples between the operations and the classes from which the objects were created. And by doing so, allowing us to define new operations without changing the code of the classes from which the objects were created. Now, the traditional implementation is the one you might be already familiar with. We will go over it, and after that, we will go over the modern implementation, the one that use records, pattern matching, and seal classes, of course. So the traditional implementation is about having an object that plays the role of a visitor because it will visit each one of the objects we have in our data structure, each one of the objects we have in our binary tree or collection, and so on. Now, on the visitor object, the object that will be instantiated from the visitor class, it would be possible to call the visit method. Let's take a look at the code I prepared for you. So the traditional approach would be we have the interface visitor, and then a class that implements it. But it all starts with the objects that create that collection or graph or binary tree. In this case, it is a binary tree. So we have the interface expression, and that interface is implemented in number. An object instantiated from the class number actually wraps a number, but expression is also implemented in multiplication, total, difference. And each one of these classes, you can see that the class implements expression, and the class includes an implementation for the accept method. So we can summarize and say that accept can be invoked on every object instantiated from the classes number, multiplication, total, and difference. Maybe instead of total, it would be better calling it total expression or expression total. And the same with multiplication, maybe calling it multiplication expression would be better choice. It is up to you. You can change the names if you want. Bottom line is that we can create, and we do it over here in our demo, as you can see, binary tree. On top, we have a multiplication object. The multiplication object holds two other expressions. So in our case, it is total object and another total object. And each one of these total objects all simple to numbers. Now, we want to go over all objects in this graph, in this binary tree. Meaning we want to go over the object that was instantiated from multiplication, but in order to evaluate this object, we first need to go over the object of the type total and the object of the type total. The other one, only when we have the evaluation of each one of them, we can go back and get the evaluation of the object that was instantiated over here from multiplication. Now, look what happens. On each one of the objects, whether it is a number object, an object of the type number, or an object of the type multiplication, or an object of the type total, on each one of these objects, we can call the accept method. And we pass over an object that was instantiated from visitor. So the visitor object actually visits each one of the elements. And when the visitor object visits a specific element, look at the implementation of accept. Look what happens. On the visitor object, there is a call to the visit method. And whenever it happens, as you can see, visit takes a reference for an object. It might be an object of the type number, it might be an object of the type multiplication, it might be an object of the type total, or an object of the type difference. So bottom line, we have more than one version for the visit method. If you check the simple visitor class, you can see that there are multiple versions for visit. So when the visitor object, an object that was instantiated from simple visitor, visits one of the elements, and it happens by passing over the reference for that visitor object to the accept method, and then inside that accept, there is a call to visit. Pay attention that the version that will be invoked will be in according to the type of the object we pass over its reference. So for instance, over here, passing over this means passing over a reference for a number, an object of the type number. So in that case, this is the method that will be invoked. Very simple. Or for instance, if accept was called on an object of the type total, then you can see, according to this code, that visit is invoked on the visitor object, and the reference of the type total is passed over. So this is the implementation that will take place. So bottom line, taking this approach means that we have a collection of elements or a graph. It can be a binary tree, and a visitor object pays a visit to each one of the elements. Paying a visit takes place by calling the accept method. So the accept method is implemented differently for each one of those classes that implement a expression. Take a look: multiplication, total, difference. And when the accept method is invoked, we can see a simple line that calls visit on the visitor object, passing over the reference for the object the visitor now pays a visit to. So it can be an object of the type number, or an object of the type total, or difference, or multiplication. And according to that, the right version of visit will be invoked, and we will get what we expect. Now, this is the traditional way. In this case, calculating the multiplication, the value of the multiplication expression of two numbers of actually 5 and 10, we expect getting 50. So if I execute this code, 50 should be the output. Now let's take a look at another way for implementing the visitor design pattern. So back to the slides. We have just seen the traditional way. We saw that we have the visitor interface and then a class that implements visitor. And on the other side, we have the expression interface and classes that implement expressions such as number, multiplication, total, subtraction, whatever. And then when you look at the code of the class that implements a visitor, then you can see that we have overloading for the visit function. So when visit is invoked, the version that fits the type of the reference that was passed over to visit, this is the version that will be invoked. Now, what happens today when we can use record classes, seal classes, pattern matching? Well, implementing the visitor design pattern becomes simpler, and I want to show you. Well, we still have the interface expression, but now in order to cover all options when we use pattern matching, you will see that shortly, we mark expression as a sealed type and specify that the only classes that can implement this interface are number, total, difference, and multiplication. And you have them, those record classes over here. Now, when you define a new class using the record keyword, not the class keyword, if you use the record keyword, then you get a new class type, but you also get automatically generated for you a constructor according to the parameters you specify, for instance. And you get also a few more things. Now, let's jump over to this program. So now I can create an object of the type multiplication, the same as we had before. Now the multiplication object that we create holds two expressions. In this case, each one of them is of the type total. and each one of them actually is the result, is an expression that its value is the result of calculating the total of two simple numbers. So the first total object should represent the value 5, the second the value 10. So multiplying the two, we expect getting the same result. But pay attention how simple it is now to go over each one of the expressions we have. And we have lots of expressions. We have an expression of the type multiplication. It holds two expression objects of the type total. Each total object is an expression that holds two other objects of the type number. Each one of them is also an expression because number, total, multiplication, all of those types implement expression. Now, in order to go over and evaluate each one of these expressions, and this is exactly what happens here, look how simple it is. We just define a class, and inside that class, we define a method that takes an expression object. Then, using a simple pattern matching and a switch case expression, switch case expression is actually a switch case, but not a statement. It is an expression, so I can return the value of that switch case expression. It is also something that was added to Java during the last years. As you can see, I'm using pattern matching in order to match the exact object that expression, the variable expression now holds its reference. So if it is a number, if it is an expression of the type number, then this is the case that will take place. If it is an object of the type total, then this is the case that will take place. If it is an object of the type multiplication, this is the case that will take place, and so on. And given that the type expression can be implemented only by the classes number, total, multiplication, and difference, because we defined expression as a sealed type, then over here, in this switch case, we actually cover all options, all possible cases. So we don't need to have a default. And so and this is where the use of a sealed type help us. Thanks to the possibility to define expression, the interface expression as a sealed type. Thanks for that, we can easily create a pattern matching that cover all possibilities. And by doing so, implement the evaluate function in a simple way, in a very simple way, so we can summarize and say that just as in the traditional implementation of visitor, implementing visitor this way, we actually succeed to add evaluation, the operation evaluate, the bottom line, to each one of the types you can see in this slide without defining it, that evaluate function separately in each one of the types. We do it outside of the definition of these types, expression, number, total, difference, and multiplication. We do it outside. We do it outside in our definition for evaluate. And look how simple everything becomes. Now, when I try to take this expression, this is not the code, just a moment. This is the code. When I try to take this expression that was created, an expression which is an object of the type multiplication, an expression that holds lots of other expressions directly and indirectly, actually the variable expression is assigned with a reference to an object which is the head of a binary tree. Now, evaluating each one of the expressions, paying a visit we can say, to each one of the expressions and evaluate each and every one of them separately becomes very simple. I just pass over to the evaluate method the reference for the object, which is the head of the binary tree, and that's it. The implementation in total, multiplication, difference, the implementation of how to calculate, how to evaluate an object of each one of these types is not in the definition of those types. The SRP principle is kept in an excellent way. The implementation of the evaluate operation is implemented outside of these types, difference, total, multiplication, and so on. It is implemented in this function, evaluate, that we define in another class. And this function this is the one that does the trick. Now, if it wasn't a binary tree, if it was a collection of expressions, then in that case, instead of calling evaluate to the head, we could have a simple loop that go over each one of the expressions, the array olds or the linked list or whatever, and then call evaluate again and again in order to evaluate each one of these expressions. Okay, now back to the slides. So this is the modern implementation of visitor, and what do we get by adopting the modern way? I think that you will agree that the code becomes cleaner, simpler to maintain. There is no need in the additional accept method. Everything becomes simpler. So that's it. And thank you for your time.